So, welcome again to digital signal processing. This is we're in the sort of mid of part of lecture 2. We should finish up lecture 2 and get into lecture 3. Depending on where we end today, we'll just make a decision as to whether or not our homework will be due on Thursday, 2 days from now, or a week from now on Tuesday. And just so you're aware, I'll show that we have the homework assignment out there. Hopefully people have had a chance to look at it and work on it. But these are the homework questions, and we ask about these block diagrams of systems, how to write down signals in terms of elementary signals as a delta function. This summation problem here is actually a very important part of digital signal processing. So there's some summation and just general ideas about signals, and then we talk about sort of complex valued exponential signals, and then this idea of sketching certain types of signals when you manipulate the sample domain. So there's a fair amount of topics to cover in order to prepare you for all of these questions in class. And so we'll see, hopefully we'll cover all of those topics. But if we don't, we'll extend the homework till Tuesday. Are there any questions before we get started? Okay then. So we're starting off with the elementary functions of digital signal processing. And you have a lot of notes that are superimposed here from the end of last lecture, where there was a question about time invariance, which is a system property. System properties are coming in a couple of lectures. But we went ahead and solved that system property discussion here, so we'll get back to that. But the actual operative part of this slide is the delta function, and this is the delta function with the continuous time variable. Here in time, it exists for just at t equal to 0, and it has a value of 1 at that location. So the digital version of it, having discrete sample index n, which is an integer, takes on a value for the integer 0 and has a value of 1. So it sort of looks exactly the same. It's not a whole lot of difference other than the fact that this is a discrete variable n, and this is a continuous variable t, and n has unit samples and t has units seconds. So moving on, we'll go to the unit step function. This is the continuous version of the unit step function. Notice everything's connected for the t-axis, and here is the discrete axis. And now on the discrete axis, you can kind of get these functions by just sampling the continuous function. So just to give you an example of like how the sampling process would go, let's assume that we have, let's assume, for example, that we have a sample period t equal to 0.2. And then we decide to sample the function u of t, and we sample it at times t equal to n times capital T to get u of nt, which when we actually substitute in the discrete index n gives us u of n. This is like how we go from a continuous function to a discrete function. So with t equal to 0.2, and we'll let n go from minus 5 all the way to 0 all the way to 5. So n times t, the product n times t, what is that going to be for minus 5? So that means that t is going to go from so it's essentially 0.2 times all these values. What's 0.2 times 5? Or
it would be 0 because it's -1, wouldn't it?
So if this were 0.2 and I multiply that by 5, I get 0.2 times minus 5, which is minus
1.
-1.
Thanks. Thank you. Right, minus 1. And so by inference, what does that mean when you multiply 0.2 times 5? 1. Okay, so where do the sample locations occur? So when n is equal to, so let's go from n equal to -5, -4, -3. This is going to be the nt is the value -1, -0.8, -0.6, and so forth. And so essentially we're taking values off at these locations here. And we're taking the value of the signal, and that's u of n. And that's how we're getting these values here. Because nt, so n has the index -5, n times t has the value -1. So we're taking u at nt, which is -1, and we're setting it equal to u of -5. So this is a value for t, and this is a value for n. So we're actually converting like values on the x-axis. So it shows you how you would sample, how this signal here would be sampled to generate this signal. Any questions on that? So not only is it telling you about the step function, which you've seen before, but it's also using our sampling equation to show you how you go from the t continuous variable to the n discrete variable. Okay, so let's talk about frequency. And specifically, we're going to talk about what we're all familiar with to date, which is continuous frequency and how it's related to discrete frequency. So again, we have a continuous function. So just like u of t, here's a function x of t is equal to sine o omega t. So we're already recorded. We're recording as it. I don't record lecture through Zoom. I record it through my OBS, and then I post the videos. So we don't need to record in Zoom. You get a much higher, well, what I've heard from all students to date is a much higher quality video produced by having video production software actually on my computer. So yeah, we've got x of t here, and it's equal to sine of omega t. Now, just one thing to establish. When we take the sine of something, the units of what goes inside of a trigonometric function is radians. Radians are things that go inside trigonometric functions. Not degrees, radians. If I have something in degrees, I convert it to radians by multiplying by pi over 180. In other words, there's pi radians in 180 degrees. So since the argument of a trigonometric function has units radians and t has units seconds, it's time, what is the units of omega?
It's
Per
second.
second. So when I multiply radians per second times second, I get units radians. So the units of frequency, angular frequency, which is omega, we call this angular frequency. The units of angular frequency are radians per second. And so radians per second multiplies by seconds, you get radians, and that product has the proper units to plug into a trigonometric function. So we sample this, and so this is how we represent the sampling process. We choose specific values of time, those values that are equal to n, some integer, times the sample period, t, right? And so n has unit samples, and so what units does t have to have? In order to, because we know t,
An integer?
n is an integer, and it's
Seconds per.
yes.
So it has to be seconds per sample, right?
Mhm.
Because if we multiply samples times second per samples, then we get the right units for t, which is seconds, right? So all of the units here need to be consistent, right? And it kind of, so we go ahead and we make this we make this substitution and we sample our signal and we generate the discrete signal with the integer index n. Okay? Now, this is our new equation, sine of omega, and now in place of t, we've substituted t is equal to nt and got this equation. Well, now the variable here, this is the variable, is n. And we have this new equation for frequency. This is the thing that multiplies. It has the variable n has unit samples. And omega t, what units does that have to have? If the argument of the sinusoid must be radians and n has unit samples, what does omega t have to have for units?
Second.
Radians per sample.
Radians per sample. Because if we multiply radians per sample times samples, we get radians. And again, radians are the things that are plugged into the argument of a sinusoid. So the units of this three-way product has to be radians. So that means that omega t has units radians per sample, and we call that little omega, and that is our new definition. This is a new thing. This is discrete frequency, or discrete angular frequency. Now, it's different from continuous frequency because its units are different. The units of a continuous frequency are radians per second. The units of discrete frequency are radians per sample. And in order to know the discrete frequency, we have to know the sample period. So if we move a signal that's a continuous sinusoid, and we sample it and move it into a discrete sinusoid, like inside the computer, its frequency changes. Its frequency changes, well, in the continuous time it was omega. It was this omega value. But in the discrete time, it's omega times the sample period, which we call little omega. And that's discrete angular frequency. Okay, that leads us to this equation, which is just a restatement of the notes that I've already written down. Little omega is equal to capital omega times t, where capital omega is the angular frequency of the sinusoid in the continuous domain, and capital T is the sample period. All right, more on sinusoids. So we just talked about discrete frequency and continuous frequency. Now we're going to talk about a discrete sinusoid with a phase. This is a phase. Since it's adding, so this and this are being added. They have the same units. What is the units of phase?
Radians.
Radians. So phase is written down in radians. So this product of omega and t also has units radians. So whenever you see something in the argument of a trigonometric function and it doesn't have any modifiers, there's nothing multiplying it, then it will have units radians. And so here we'll see a cosine that's just slightly shifted. It has a peak that's just after, so let's see, at 0, it's got this value here. So you might say that it's got a phase shift. This would be its normal peak, and phi is shifting it here. So phi is moving that signal along the time axis. So realize that any phase shift you might have is equivalent to a phase shift like this, where you're taking phi plus 2 pi, right? And so phase shifts do not, so any cosine that you have, cosine of omega t plus phi is equal to cosine of omega t plus phi plus 2 pi, because this 2 pi doesn't change anything. If you take any value that's inside of a trigonometric function, you add 2 pi to it, well, cosine and sine, they're 2 pi periodic. That means that they'll take on the same value 2 pi radians later. And so it also doesn't matter how many times you add 2 pi. So if k is an integer, you can add 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, minus 10 pi, minus 12 pi, any multiple of 2 pi, positive or negative, and it does not change the value. So now similarly, this unit, what are the units of phi here?
Radians per sample, right?
No, that's the unit of omega. This guy here is,
Radians.
again, this
Radians
is
still?
it's still radians. It's still radians, and that's why it's kind of like some things are changing, but other things are not, which is why I kind of ask that. So, in this particular case, we know that the phase delays that you add into these sinusoids have the same units and operate in the same way. But the frequencies that we see here are the things that ultimately change. This omega and this little omega are different by the relationship that little omega is equal to capital omega times the sample period. And this shows you a sampling of a cosine. So it's exactly the same paradigm that we had before. In this particular case, the value of capital T, this is cosine so this is x of n, what that you'll get by taking x of t and sampling it at locations t is equal to n, where capital T is equal to 1. So the interval between samples is exact. So you can see that we're getting the interval between samples is 1 second, and that's why the sample value that you see here is a sort of the same sample value that you see here. Any questions on this? All right. Periodic sampling. So again, we're talking about the sampling process, but the sampling process is actually a periodic process itself. So T has the units seconds per sample. So we're saying how many seconds expire between one sample and the next. So it's periodic. So the sample process actually has its own frequency, and that frequency can be represented in hertz, which is cycles per second, or it can be represented as an angular frequency in radians per second. And this is a conversion factor from hertz to angular frequency. And so this just says that there are 2 pi radians in one cycle. So using that conversion, these equations I am hoping you've all seen before. 2 pi radians per cycle times cycles per second gives you radians per second. So this equation you can just see as a units conversion. That's sort of how much of these equations you don't really need to memorize if you just know what the units of things are. All right, and so the most common sampling is a periodic sampling, where the intervals between one sample and the next is exactly the same. And in this case, T is called the sample period, and Fs, which is 1 over T, is the sampling frequency in hertz. And so the sampling frequency in radians per second is omega s equals 2 pi Fs radians per second. And again, we're talking about, we're using the brackets here, so the brackets to denote a discrete time function, and we're using the parentheses here. That denotes a continuous time function, or a continuous signal in general. Whatever's inside the parentheses must be a continuous variable. Whatever's inside the brackets, this is a discrete variable. Like integers are discrete. They occur at specific locations and are not continuous. They jump from one integer to the next. All right, so in general, sampling is not reversible. Well, you have a continuous function. And so a continuous function, by definition, you can take any infinitesimal interval from it. Say we have a function here, we take some infinitesimal interval, we'll call it epsilon. There is an infinite number of values on any infinitesimal interval that's non-zero in length. So when you sample it, you're discarding an infinite at any rate, no matter how quickly you sample it. If your sample period is actually finite, then there'll be a finite interval from one sample to the next, in which inside of that interval the continuous function will take on an infinite number of values. So because of that, we're losing information. And so when you sample, you lose the information, which is all of the values of the function in between the sample locations. And so if we were to reconstruct that signal, say I have an audio signal, gets sampled, sent over the internet, reconstructed and sent out to your loudspeaker, it's not going to be exactly what was there unless it satisfies very specific criterion. And so the fundamental issue in digital signal processing is that we lose information during the sampling and we cannot recover it. So one of the fundamental outcomes of this course will be to understand that there are certain conditions where an analog signal can be sampled without loss. So if we constrain how we sample and we constrain the structure of the signal, we can undergo the sampling process of digital signal processing and be able to reconstruct the analog signal without loss. That's sort of like a magic trick. It's like a magic trick, but it becomes less of a magic trick once we understand theoretically why that can be done. But that is one of the fundamental outcomes of understanding the theory of this class. So in those circumstances, we can reconstruct the original signal perfectly, which is fairly amazing. All right, so here's a sampling example. And so this is lecture 2. So I'm going to try and get my MATLAB to work with me. Everything is in gray here, so I'm just going to ignore that and click. And so here we have the MATLAB associated with the lecture, and you can see the elementary functions on the right-hand side here. And it has, the equations as well. And then, actually has some related stuff to homeworks and stuff. Like these are things that you'll see in the homework. So some of the signals and stuff you'll see. So I just wanted to sort of point that out. And here we have a MATLAB program that's going to sample a sinusoid. So the first thing is that we'll write down the frequency of the sinusoid in hertz. So this is 60 hertz. That means it's 60 cycles per second. Anyone familiar with something that oscillates at 60 cycles per second? AC. Yeah, thank you very much, Nick. That is correct. So this might be the kind of sinusoid that would come out of a single-phase outlet for powering everything in your home. And so I'm going to go from the time min is 5 hundredths of a second to time max, which is positive 5 hundredths of a second. So minus 5 hundredths of a second to positive 5 hundredths of a second. So that's the interval of the time axis from the beginning to the end. And linspace is going to divide up that interval from minus 0.5 to 0.5 into 400 increments. So 400 steps. This is the number of steps to traverse that interval. So it's a 0.1 interval on the real line on t, and this will create a sequence of values of t that are going to traverse that interval. So then I take the signal values and I just evaluate them. So t is actually a vector here. So t is a vector that's 400 by 1 vector holding the values. And so when I plug t in as a vector, this is going to give me another vector which is 400 by 1. So it's a list of all of the values. Now when I call plot, this is a continuous plot, so it connects together sequential values with a line. And that gives us this line. And so you've seen these things in both 2254 and 3111, and this is just kind of a review. Now when I put this X label on here, that actually puts this label for the X-axis on my plot. And so the MATLAB is available to you, and it's just... Let's see if so these are examples of how to write a step function. I actually have a lot more detail in my plots, so I'm just not going to go over them in detail, but you certainly can download them and run them and ask any questions that you might have about them. Any questions on any of this material? Okay, here's another sampling example. And in this example, we've got a continuous frequency that's, what do we have here for our frequency? I guess f has the same value, so I'll go ahead. Well, this says sampling frequency of 800 hertz, right? I think that maybe f is still 60 hertz, so it's not on the slide, but so t is 1 over 800. Okay, so that means that fs, the sample frequency, is 1 over t, which is 800 hertz. And then what we're doing there is we're just going and plugging in n times capital T. Now n goes from some index t min divided by capital T to t max divided by capital T. So we're actually calculating the value, the smallest value of n that corresponds to when so when t min is equal to 0.5 minus 0.05, we divide that by capital T and we'll get the corresponding index of n, because remember we have this relationship t is equal to nt. So then if you have t min is equal to n min, the smallest index in n, times t, and then you can take t min divided by capital T and you'll get the smallest index of n, right? N min is equal to t min over capital T. And same for the max. So that's what's being calculated here, and here is just the index that I need for n's. It has to start at n min and go to n max. And so then, instead of plugging in the values of little t here, I can plug in the values of nt, and I'm using the relationship t is equal to nt. And this shows that when we sample this, now I'm plotting as little circles, so as dots, the values of our samples. So you can see them. I'll circle them to make it more clear, but the little red dots are the locations where we've sampled the signal. And they're all over the place. But that's what you get when you sample a signal at 60 hertz at a rate of 800 hertz. So in this case, we sample it at 400 hertz. Everything else is the same. So now we have a sample frequency of 400 hertz. So when we're sampling at 400 hertz, so the sample period is twice as large. 1 over 400 is 2 times the size of 1 over 800. And you can see that here you have a sample here, here, and here. But now when you sample at 1 over 400, you only have a sample here and here, and that intermediate sample was skipped. We are doubling the space between samples. So that means that every 2 samples from the signal above corresponds to a single increment from one sample to the next in this signal. It gives you an idea of how signal samples are related for different kinds of sampling rates. Finally, we do 120, and we sample it at note that 120 fs is equal to 120 hertz, and that's actually equal to 2 times 60 hertz. It's really the lowest you can. We'll learn why, but you don't want to sample at a rate lower than this, because we're taking a sample at the peak and the trough, and the peak and the trough. We're getting exactly 2 samples per cycle on the entire signal, and you can see the sample locations here, and so forth and so on repeatedly. And those are different ways of sampling a sinusoid. You try 70 hertz and you get a slightly different distribution, and you actually see that the samples themselves are actually having a pattern that's sinusoidal, but that sinusoid is actually a lower frequency than the 60 hertz sinusoid, which is ultimately something called aliasing. We're sampling a 60 hertz sinusoid, but what we get out looks like a sinusoid having much lower frequency. You can consider this to maybe have come from a sinusoid having this frequency. And so this frequency is lower than 60 hertz. And so when you start sampling at rates lower than twice the frequency that you have as input, then the signal sort of appears as a frequency other than what it should. Okay, and so this is an example of the aliased signal when we actually sample at a lower frequency, right? We sample at 1/70, we get this cycle here. This looks like a 10 hertz signal, but the samples are from a 60 hertz signal, so the 10 here isn't exactly clear. Let's go ahead and from a 10 hertz signal, but the samples are from a 60 hertz signal. And so this is an example of what you don't want. You sample the signal and it now looks like a signal different from the signal that you had originally. This typically happens when you sample at a rate that's too slow, or the amount of time between one sample and the next is too long, or your sample period is too large, or equivalently, since frequency is the inverse of that, your sample frequency is too small. All right, that's it for lecture 2. We're going to move on to lecture 3. So I'll save this. Any questions?
I have one about the lecture 3 PDF. If we could have access to it.
Yeah, of course. So sorry for that. I will go ahead and rectify that right now. You should have access to it now.
Thank you.
Yeah, so it should be available for you right here as lecture 3, as well as I'll have to unlock. I think the video content might be locked. I'm going to go and unlock that after class, as hopefully you'll stay here with me in actual lecture. So let's see. Lecture 3. Let's go ahead and get started on that. So I've already deleted and re-uploaded all of these so that the annotations are gone. So of course we have homework available, and we do have as of right now a quiz for Thursday. We'll see how far we get. I'm hoping we get through lecture 3. All right, so this is from the textbook. This is sections 2.2 to 2.5 in the textbook, and we're talking about discrete time signals and their behaviors. All right, so the first and actually the most important discrete time signal is the complex exponential. All right, so this is the real valued exponential, which is a subset of the complex exponential, but it looks different from what we might be used to. All right, I call this an exponential signal, but we are very used to seeing e to the minus t or something like this, e to the minus alpha t or something like that. This is something we deal a lot with in terms of continuous theory, and so e is just a number. E is just a number. So let's write this out a little bit. So what's the exact value of e? Value of e. All right, so 2 points. It's just a number, and it's actually a very, very interesting number. And e is Euler's number, and it comes up everywhere. I'm just going to write it down as 2.72 for now, but it's got more digits. It goes on, and it comes from this this expansion, this infinite series sum. That's where the number comes from, and it arises all over the place in nature, all over the place. In fact, every single differential equation you've calculated a solution for, well, except for undamped oscillating systems, has this. In fact, that has this number in it. It's all around us. It is part of how our world works, because differential equations model how physical processes and systems operate in our world. They all have this e, which is 2.72, well, as an approximation, so it's approximately equal to this. that number in them. And that should be fascinating to you. I find it fascinating myself. But I've written down the exponential signal here slightly differently. All right. And this is because e is a number. All right. Sure, we can make alpha equal to the value e. But in discrete signal processing, in digital signal processing, often alpha doesn't have the value e. Often it's like 1, 2, 0.8, right? And so we go from this idea of e to the minus alpha t, or let's just call it e to the minus at, because I'm e to the minus at, and we call it something like alpha to the minus at. You can put any number there as the base of this exponent that is exponentiated by minus at. And there's a couple other trigonometric, and in this case, alpha would have the value e, right? And there's a couple of other properties I want to point out at this point, because if you have something exponentiated to the minus at power, you can write it a lot of different ways. Algebraically, you can write it as alpha to the t to the minus a. You could write it as alpha to the a to the minus t. And you can take the minus inside or outside of that as you like. And we use this kind of algebraic. This is algebraic things that we can end up using that are important to know about, algebraic relationships. So that's a little bit just about like the exponential function and how it comes up. Here in discrete signal processing, we talk about it as some number, alpha, to the nth power, where n is an integer. So we're talking about powers that are, integral powers. Now, a is some arbitrary constant out in front. Now, if a and alpha are both real values, then we get exponentials as we've always known them, albeit the base is arbitrary, right? So if alpha is real value, there are three behaviors that can happen. When alpha is greater than 1, then you're going to have something that grows. So this alpha greater than 1, this is the absolute value, or the magnitude of alpha is greater than 1. That's this. Here's alpha equals 1.1, and then this is alpha to the n. Alpha to the n grows. So then there's alpha equal to 1. Well, when alpha is equal to 1, 1 to the n is always 1. Right? No matter what value of n, so this corresponds. So this plot here corresponds to alpha to the n. Now, when alpha is less than 1, we're going to have, this is magnitude of alpha is less than 1. We have alpha equal to 0.9, and it's a decaying exponential. It grows when it's negative. It decays when n is positive. It's sort of the time reversed value of this. So it's flipped across the origin here. Finally, if you have a negative value for alpha, it's going to oscillate. So take any one of these signals, and if alpha were negative, every odd indexed sample would be negative, the negative version of that value. So it'll oscillate back and forth. So we now see that real valued signals can exhibit oscillatory behavior. So this is an oscillating function. So this is sort of, well, there are three different appearances for alpha positive, and then you can take if you make any of those alphas negative, they all of a sudden turn into oscillating functions. So sort of 6 different kinds of signals that you can see for just a real valued exponential signal. So exponentially decreasing and not oscillating, exponentially decreasing and oscillating, exponentially increasing and not oscillating, exponentially increasing and oscillating, and then constant and not oscillating, and constant and oscillating, say if alpha were equal to -1. So there's 6 faces to the real valued exponential signal. Let's talk about what happens when a and alpha can be complex, not complexed. So if a is complex, so this is like a quick review of complex number theory. which is incredibly important for this class. And you've seen in a number of classes, you've seen in both, you have a comprehensive review of this in 2254, you see it again in 3111, and you see it, if you're an electrical engineer, twice after that, both in 3122, 3121, even the power 3142, as well as other areas. But we've seen it several times. Very important to keep hold of those complex number theory skills. So we're going to represent a complex number A in the polar representation, which has a magnitude R and a phase component phi. Now, a complex number in the complex plane, there's in fact 3 quadrants or quarters to the complex plane. The complex plane measures on the x-axis the real value of a complex number as the x value, and the imaginary part of the complex value as its y value. And if we have a coordinate, a complex number, z is equal to a plus jb, that means we move out on the real axis a and up on the imaginary axis b. And this sets up the geometry of complex numbers in the complex plane. So this is the complex plane. And this is a complex number z naught in that plane. Well, we can represent z naught in the so-called Cartesian representation. This is sort of a 2D representation of x, sort of like x and y. It's established by Descartes. Or we can represent it in polar format. And the polar format is simply representing it in terms of an angle. This is called the phase. And the magnitude. This is r. This is the magnitude. And so we can get to this location in the plane by taking a point, going out on the real axis, a distance r, and rotating counterclockwise by phi. That will get us to this location. That's one way to get there. You go out to here, and then you rotate there, and this the tip of the arrow will go there. The other one is to just go out on the real axis A and up B. So it's kind of like a I'm going to walk along the city blocks. I'm going to go along this city block at distance A and up this city block at distance B and get there. It's just 2 different ways of getting to the same point, and they're in 2 different coordinate systems. Is there any questions whatsoever about the coordinate systems at work here? Okay, so a very important relation that's part of these coordinate systems is Euler's formula. So again, I'm just going to quickly go over a plus jb, the magnitude of a. If we use Euler's formula, which is written this way, you can see Euler's formula as just a trigonometry 101. So this point here, so if we're taking the cosine of phi, what is the cosine of phi here in this trigonometry problem? So cosine of phi is the adjacent versus hypotenuse. So it's a over the magnitude of our complex number. Sine of phi is the opposite over hypotenuse, which is b over magnitude of a. And so we can represent a complex number as cosine, like we could say magnitude of a times cosine of phi. That's where our x coordinate is. Sorry, I've got overwriting some things. Magnitude of a times cosine of phi. This quantity here is equal to a. And then we can say plus magnitude of a times sine of phi. That's equal to the quantity b. So if we do j times that, we have a plus j times b. And so they're both a way of writing down the coordinate z naught. Now if the magnitude of z naught is equal to 1, then a is equal to magnitude of a is equal to 1. And then we have cosine of phi plus j times sine of phi is equal to some complex number on the unit circle. So it's r e to the j phi is equal to magnitude of a cosine phi plus magnitude of a sine phi. But if that magnitude is equal 1, if the magnitude of a equals to 1, then r is equal to 1. Then you have e to the j phi is equal to cosine phi plus j sine phi. And we've actually proved, just using trigonometry, Euler's formula, right? There's nothing fancy going on here. We're just using trig. And so this formula can be thought of as just an exercise in trigonometry. This is the relationship between, this just a way of charting different points on the unit circle, the points that have radius 1 away from the origin. Any questions about complex numbers? Now the way to actually get back phi, so phi itself, can be represented sine of phi over cosine of phi is equal to tangent of phi, right? And that's equal to, well, if we divide sine of phi, which is b over magnitude of a, so that's b over magnitude of a over a over magnitude of a. The magnitudes of a cancel. You get b over a, and so that's the imaginary over the real. The imaginary component b divided by the real component. That means that you can get phi back by tan inverse of b over a. And so you usually want to use a tan 2, which is a arctangent function that is aware of all 4 quadrants. So that is a quick review of complex number theory. Is there any questions about complex number theory or Euler's formula? All right, I'm glad to hear that everyone's confident with their complex number theory. That means we should also be able to add, subtract, multiply, divide, and all complex numbers, and be able to convert them between one representation and the other, polar to Cartesian, Cartesian to polar, and so forth and so on. All right, the exponential signal, part 2. Now the exponential signal has a new face. We actually allow alpha to not only be real, but now complex. E to the delta naught plus j omega naught. So delta naught is the real part of a complex number, and omega naught is the imaginary part. So now alpha can take on an imaginary component. So we write out the same thing that we had before. So we have a complex function. And then we wrote down, remember, x of n is equal to a alpha to the n. So now alpha has this representation. So we represent a in terms of its magnitude phase format. So we represent a as its magnitude and its phase e to the j phi. So we're putting a in polar format. And now we take this property and we say that we can represent alpha to the n is equal to alpha to the n. Now I write it like that so that we can kind of make sense out of this. We can put this to the n. If we put e to the delta naught plus j omega naught, and then we take it to the nth power, then the n distributes down in. This is equal to e to the delta naught n times e to the j omega naught n. Or I've actually written them as a sum, right? So I've written them as a sum there, and then I broke apart the sum there. So you can understand all of these algebraic steps that are occurring here. So having done that, we can take the phase component that's present in A and the phase component that's present in omega naught n and combine them. And so we get that term there, all right? We get the real valued component there. And now we're going to rewrite that. We're going to apply, so we apply Euler's formula. So e to the j omega naught n plus phi. Well, if we look at just up here, right, when you have phi, you get cosine of phi plus j sine phi. Now phi has a whole new value. It's this entire expression. This entire expression. So now we write this down as a times e to the delta naught multiplied by n. And now we have cosine of omega naught n plus phi plus j sine of omega naught n plus phi. And now we start to see the oscillatory behavior. From all this analysis, we can see the oscillatory behavior. So on the front here, we have our real valued exponential signal. So all of the behaviors we previously talked about for real valued exponentials manifests in this signal through this term. Then we have additional oscillatory terms. One for the real component, which is this term, and one for the imaginary component, which is this term. And so each one of them has this real valued exponential multiplying into it. So you get different kind of oscillatory behavior. And so here's several examples of what that looks like. And we've got here are actual plots for the complex behaviors here, where we have different complex numbers. Now note that you can actually use j in MATLAB to represent a complex component. So as long as you don't define the variable j, so like if you say j is equal to 1 in a line of MATLAB code, it's no longer interpreted as a complex number. So you have to make sure that you don't have any code that redefines j or I, and then you can use it to represent the complex component of a complex number. And so the MATLAB for this stuff is all available here, and you can see it there. So having said that, when I say, are there any questions about any of this mathematical manipulation we've been doing?
Dr. Willis, I have a quick question. You can go ahead. Sorry, dude.
Oh, you're good, Eric. Go ahead. You might be covered.
Oh, I'm probably going to ask a silly question here. But we're not going to be dealing with hyperbolic functions in this class, are we, Dr. Willis?
Yeah, we won't be dealing with the hyperbolic function. There's no, I don't recall that coming up in any context. Albeit they are important functions, just not functions that commonly come up in DSP.
Gotcha. Thank you.
And so what Eric's referring to is a hyperbolic. There are hyperbolic forms of, in fact, every trigonometric function. So hyperbolic trig functions. And so they're very interesting. So there's a hyperbolic sine, hyperbolic cosine, hyperbolic. So sine h, cosh, tan h. Secant, every trigonometric function has its analog as a hyperbolic function. Why that's the case, we're not going to get into, but it's just kind of good to know about from just like being exposed to all corners of the mathematical realm. But it's not going to come up very much for our class. There was another question. Was there another question? Okay, so I'm going to continue if there wasn't.
No, I'm good.
Okay. Periodic.
I think somebody asked a question in the chat.
Yeah.
Oh, digital notch filter uses hyperbolic theory. Yeah, there are filters out there for sure that you can apply hyperbolic theory to. It's just not going to come up as a part of our undergraduate class. So it comes up quite a lot, and I can think of like 3 different contexts where the hyperbolic functions come up in filter theory. But I can't think of one context where it's going to come up in the context of a digital signal processing class where we're talking about the fundamentals of signal processing. let's see. So periodic signals. So I hopefully that this is no surprise. We've seen periodic signals, but periodicity exists in both the continuous and the discrete domain. So when we talk about a periodic signal in the time domain, like a periodic signal in the time domain, a periodic signal in the time domain, a periodic signal in the time domain. Well, I just said that 3 times. That was a periodic signal in the time domain. The time it took to repeat itself would be the period. And the fundamental period, which we kind of talked about in our last lecture, is the smallest value of capital T where it's true. So that the same analogy holds for discrete functions. But here, it's a very, very important difference. All right, so T, this is a braces, this is parentheses, right? So that means that T, these are continuous variables. So that means that we have the possibility for T to take on arbitrary irrational numbers in order to achieve to repeat itself. In other words, say I write down sine of T. What is the period of sine of T? When is it going to be equal to itself? Sine of T plus 2 pi, right? Any sine is going to be periodic with period 2 pi. In fact, it would be true if I wrote it down as sine of T plus 2 pi k for any integer k, right? It would be k is an integer. These are all true statements for a continuous variable. But say that I have the same thing for a discrete variable. The point here is that n is inside the brackets. So anything inside the brackets is an integer value. So n is an integer, and students commonly forget this and solve for a period and give a value of n that isn't in fact an integer, and it can't possibly be the case because this is a discrete function, and a discrete function is only defined at integer locations. We can use conventions to define it elsewhere, but this is its formal definition. And so in this particular case, we show a cosine function, and it repeats this sample after 7 samples. So 7 is an integer, and so this is a valid kind of periodicity for a discrete function. But we'll find some surprising results of this analysis. So let's talk about sinusoids. Now we know that any sinusoid is periodic in the time domain. So if I come up with x of t is equal to sine of omega t, and I want to find out its period, I can write x of t plus capital T. Okay, and that's a sine. I have to plug in t plus capital T for where t was in there before, so omega t plus capital T, and this is if this is going to be true, we have to find a relationship between these two. And so it proceeds fairly straightforward way. So sine of omega t therefore has to be equal to sine of omega t plus omega times capital T. But that can only be true if omega t times capital T is equal to some multiple of 2 pi, like 2 pi k. So any value of the period has to be 2 pi over omega, and so this would be the fundamental period, the smallest value for any, and then k gives you all possible correct values for the period. And so that's how you solve for the period for a sinusoid. It's just that simple. You just use the definition. Well, we find something surprising here, my friends. We do the same exact process. Okay, so we write down. Let's see. We're going to see what's the period of this signal. We're going to use the exact same process that you do in the time domain. So we write down the signal itself on the left. This is the signal, and then we write down the signal where we have n plus capital N in place of n on the right, and they have to be equal in order to solve for the period. So then we have omega naught n plus phi has to be equal to omega naught n plus phi plus this term here, omega naught times capital N. Now, in the same exact way that we did for the continuous time, we must presume that the product omega naught n is some multiple of 2 pi k. Otherwise, these two things cannot be equal. And in such a case, that implies that the true period is 2 pi, which is capital N in this equation, is 2 pi k over omega naught. Okay? Now, n has to be an integer. I'm going to say this a number of times during this derivation. So if we've got 2 pi on the right-hand side. So, and k, we also know that k is an integer. It's some multiple of 2 pi, right? Well, this can only be an integer. What does that require of omega naught? To just get rid of the pi on the right-hand side.
Have to be in the radian.
Yeah, omega naught has to have a pi in it. It has to be expressible as a times pi, right? It has to contain pi. If someone says that, thank you. Otherwise, the pi's don't cancel, and n can never be an integer. What does this imply about? Let's say that x of n, sine of n. That has to be equal to sine of n plus capital N. And so, well, that means that n has to be so what's omega naught? Omega naught in this case is 1, so omega naught is 1. And then using our formula, n is 2 pi k over 1. So is there a value of n that is an integer value that satisfies this relation? Does a k exist such that n is an integer?
No.
Okay, excellent answer. Correct. So what does this imply? If you take a discrete function, sine of n, it never, ever, ever repeats its sequence of values. It is not periodic. Okay, I saw that for the first time and I was like, that's a surprise. So when you sample periodic functions, they're not necessarily periodic, because I can tell you sine of t is periodic, and we talked about it earlier in class. Its period is 2 pi. It repeats when for a sample. This has a period of t equal to 2 pi, but of course 2 pi is an irrational number. So sine of n never repeats. We're only evaluating it at integer locations. N never ever repeats. That's a surprise. Okay, so then we can start asking questions. What kind of number does omega naught have to be? And this gives you sort of the, I can always solve for the period of a discrete sinusoid if I do the following 3 steps. So as I go through class, I will give you these things called techniques for solution. This is the way that you go about solving a problem asking you for the periodicity of a discrete sinusoid that will never fail. Absolutely cannot fail. It contains 3 steps. First, you have to manipulate the frequency to have units radians per sample. So if you get the frequency in hertz or in some other representation, you have to get it into something that is represented. You use relations like omega is equal to capital omega times t. You use relationships in time and frequency like t is equal to nt. And you come up with your frequency, your discrete frequency omega naught. Then you have your equation. Your equation says that n is equal to 2 pi k over omega naught. Well, this has implications. We've already found that omega naught has to have a factor of pi in it. If it does not have a factor of pi, then this function is not periodic. Further, it can't be an irrational number times pi. It has to be a rational number. All right? So I'm going to represent that rational number as a over b. It has to have the form of a rational number times pi. Otherwise, the signal is aperiodic. All right. Now, if omega naught is represented as a rational number times pi, then we just plug in that to our equation. We say 2 pi k over some rational number, a over b, times pi. The pi's cancel. And we get 2 times b over a times k. And now that gives us this equation. We must reduce the fraction, so we reduce this fraction by canceling any common factors, and then choose an integer k that cancels it with the irreducible denominator to find the fundamental period, or the smallest valid value of n that makes this relationship x of n is equal to x of n plus capital N true. That is how you find the period of a signal and that process cannot fail. Any questions?
Or do you mean by after you reduce the fraction, you find the value that get rid of a?
Yeah, you have to get rid of a because a is not integral, right? Say
Okay.
let's go ahead and say that we have a sine of 0.2 n. So what is omega naught here? So what is the value of omega naught?
0.2.
Oh, 0.2.
Yeah, 0.2. Okay, is this periodic or not periodic right away?
Nah.
Does it have a multiple of pi?
No.
No, it
Oh, it is not.
doesn't satisfy step 2. We already know it's not periodic. Okay, now if I write 2 times pi, 0.2 times pi, so omega naught is equal to 0.2 times pi. Then you have 2 pi k over 0.2. Is 0.2 a rational number? 0.2 is equal to 2 over 10. It's the rational number 2 over 10. Anything that's not a repeating number, right? Like a 0.3 repeating, or anything that you can write down that doesn't involve explicitly repeating numbers is going to be a rational number, right? So we write that down. So it's 2 over 10 times pi. So the pi's cancel. We get 20 over 2 times k. Then we reduce the fraction and we get to 10 times k, but there's no irreducible factor in the denominator. So what is the period of that function? We let k equal 1, and then n is equal to 10, right? And so that's an example of how we go about calculating the period. Any other questions before we go on?
Yeah. So why did we make the assumption that k was equal to 1 again?
Because what we do is we reduce the fraction, so this part here, right? Once the fraction is reduced, we choose an integer value k that cancels with the irreducible denominator. So in this case, this was 1. The denominator is 10 over 1. So k is equal to 1.
Gotcha. Thank you.
Yeah, so like if you couldn't reduce the denominator, say that there was like a 3 or a factor of 5, then you let k equals whatever that value is. And that's then they will cancel. K will cancel with that denominator and give you an integer.
Makes sense. Thanks.
Okay. So here's another example. I guess in this case we chose 0.25 pi. Is this going to be periodic?
Yes.
Yes.
It's right. You can write this as 25 over 100 times pi. So we already know it's a rational number times pi. It's definitely going to be periodic. And so how do we proceed? Well, we write 2 pi k over 0.25, which is this is omega naught. And then we calculate, so 25 is 25 over 100, so that gives you 200 over 25. We reduce that. That ends up being 8 over 1. And so we let k equal 1, and the value of the period is 8. And so again, one of the surprising things that I've already pointed out is that sine of n, not periodic. Not periodic. Wow. It's kind of surprising. Okay, symmetry properties. So there's even symmetry. So we same thing that we did in signals. So even symmetry looked like this in signals, and it looks like this in discrete time. Odd symmetry looks like this in signals, equals minus x minus t, and it looks exactly the same in discrete time, but just our variable is discrete. So this is odd. So any all real signals can be written as a sum of their even and odd parts. So any signal x of n that's a real valued can be written as a sum of its even and its odd part. And this programmatically, you can break it down into its parts by using these equations. You can get the odd part by taking x of n and subtracting its time reversed values. Now, when we time reverse things, we're basically taking everything on the positive axis, moving it to the same index on the negative axis, and vice versa. And so this involves flipping the sign of those values as well. And then this is how you get the even version of a signal. So you basically take the signal, time reverse it or sort of fold it flip it across the origin on the x-axis and add it to itself and then multiply by 1/2. And when you negate the values, you'll get an odd signal, which is this case here. And when you do not negate the values, you get an even signal. And so here's a original signal here. There's the flip signal there, so it's time reversing. So the value that was here ends up being here, and the value that's here moves to there. So the value that was at 1 moves to -1, and the value that was at -1 moves to 1. And this is consistent for all of the values. Notice the value at 0 does not move. Then we add it to itself. If we add this and this, we get this signal. And if we subtract these two signals, we'll get this signal. And that's how you get the even and the odd components of a signal. All right. So we move on out of the real domain and into the continuous domain. Into the complex number domain, and we extend these concepts. So the concept of even is extended to conjugate symmetric. Right? Conjugate symmetric implies that the real part is even, and the imaginary part is odd. So when you have complex signals, that's what's implied by conjugate symmetric. Conjugate antisymmetric implies that the real part is odd and the imaginary part is even. And as you might expect, because the real part and the imaginary, so since the even part and the odd part of a real function can be added to regenerate the signal, well, if you take the conjugate symmetric and conjugate antisymmetric part, you'll have the even and the odd part of the real signal and the odd and the even part of the imaginary signal respectively. So that means that any complex signal can be calculated as the sum of the conjugate symmetric part and its conjugate antisymmetric part. And the way that you calculate them is exactly the same, but you use conjugation. Now, just to recall, if you have a complex number, z plus a jb, its conjugate, z star, is equal to a minus jb. So we're just negating, we're flipping the sign of the imaginary component. Any questions on this? Let's see how we're doing here in terms of slide progress. So we're sort of halfway through. Yeah, I think I'm going to extend the homework to Tuesday of next week. I'd like to get through this and maybe even a little bit of the next lecture. So we'll have an extension in the homework as we're really at the end of lecture here today. I haven't gotten all the way through lecture 3. It just should well prepare you for a lot of the content of the homework, and not quite everything. I do want to tell you a little bit about the geometric sums. So we'll extend the homework until Tuesday. Go over one more slide, which is actually pretty trivial. We're saying that we can do arithmetic signal operations. We can add signals together. This is talking about a whole signal. So this signal exists for all values of n. And so we can add them. That's superposition. We can multiply. When you multiply them, it's often called modulation. Or you can scale them and just multiply a signal by a constant. And this starts to get us into this idea of an input-output. So here we have two signals that are going in, and the output is called y. We have two signals that get multiplied, and the output is called y. So this kind of idea that when you take x of n, it goes into a system, generally t, something happens to it, and then different numbers come out, and we'll call that y of n. This is the system representation, and so this carries on from signals and systems into this class. In our next class, we'll go through all manipulations of the variable n. So you can delay signals, you can advance signals by shifting them left and right, you can stretch them out, and you can make them shorter by multiplying by n. You can do all sorts of interesting things to signals by manipulating the inside, the argument of this function. I call them manipulations of the time variable. That's where we'll start for next lecture. We're going to wrap things up here since we're out of time. And again, the homework and the quiz will be moved to Tuesday of next week. And if you have any questions, stay after and ask. So if you don't, you're dismissed, and I hope you have a good afternoon.
Thank you.
I'm going to stop the recording at this point. Thank you. And I'll stay if there are any questions. The quiz will test you on everything that's in the slides, as well as related concepts that are actually in the homeworks and stuff. It's the slides and the content, the technical content of the homework questions and the reading as well. But ultimately, it really emphasizes the homework and the slides. Thanks everyone. Thank you. Stop recording. Stop.